All right, can I have everybody's attention? Want to introduce our speaker for today. We have Mark Mattingly. He's here from the NASA Johnson Space Center and the Orbital Debris Program Office. And he's also an alumni of both Texas Christian and Rice University for his PhD. And also, I guess you saw in the abstract, we also had Russell Graves mentioned on here. He was another person in the Orbital Debris group who was from Boeing, the industry side. And he's actually out of the country right now. So with that, I want to turn everything over to Mark Mattingly, and I'm also going to be passing around a sign-in sheet so you guys can just sign and move on.
Thank you, Graves, for this. I'll correct your pronunciation. It's Matney, but no big deal. That's right. I've been known by many, many things, some of which I probably don't like. So, like I said, I got my bachelor's degree from TCU in 1985, and my PhD in Rice in 92. I was in Space Physics Astronomy Department. I understand you'll have Pat Rice spoke. She was one of my professors at Rice, so she and I go back way back. Ever since 1992, I've been a member of the Orbital Debris Program Office at NASA Johnson Space Center. It wasn't called that in those days, but it was. But I worked for Lockheed Martin for many years and been a civil servant, a government employee, 8 years, something like that. So I am the modeling lead, is my official title. Well, that means I don't do modeling, but I'm sort of a jack of all trades. I do a little bit of everything. And we'll talk a little bit about orbital debris. I find that people find the subject very interesting because it's sort of a little bit of everything, and everybody's fascinated, everybody has an opinion, everybody has an idea. So hopefully you'll learn a few things today, and you'll find it interesting. All right, first question is, what is orbital debris? There's a long history about the definition. The Europeans refer to it as space debris. Space debris is kind of new. Orbital debris is specifically the name we give it is human-made debris. There's another kind of debris, part of the expression, is natural debris. One man's debris is another man's treasure. But in our case, we're mostly talking about artificial man-made particles. Now, through the years, I have done work with micrometeoroids and meteoroids and asteroids and things like that with colleagues, but that's not my major emphasis. It's kind of a fun diversion, and there's a lot of overlap in our different fields. But my bread and butter is orbital debris, human-made stuff. Again, meteoroids are natural objects in orbit about the sun, and orbital debris is any man-made object in Earth orbit that no longer serves a useful purpose, which is a little bit of a vague definition, but it makes sense. Trash. And then one of my favorite phrases is all man-made objects in orbit are destined to become debris in one way or another. That's the trouble with technology. Every piece of technology is destined to become junk one day. It's the way it is. And just to give you the idea that we have non-operational spacecraft, we have a number of spacecraft that were launched, they're still in orbit, no longer function, they don't longer own home. We have a lot of derelict launch vehicle stages. Those are often used to put spacecraft in orbit and are immediately abandoned in orbit. And the most pernicious is fragmentation debris, also something called mission-related debris. Those are brackets and things, relatively minor contributors. Fragmentation debris, we'll talk a lot about that today. That turns out to be a big deal. I got some cartoons for you guys. I love cartoons. My favorite, if you read the Chronicle, is Brewster Rocket. You guys read Brewster Rocket? Oh, you got to read Brewster Rocket because it's always science fiction, and every week or two there's NASA references in it that we're there. And every time we're in the news, 2 weeks later, Brewster Rocket has something about it. I'll show you more. But I forget the lieutenant's name here, but she says, according to NASA, space junk has become a problem. Years of debris from space missions accumulating around Earth since it's enough to hold clubs and forgotten spacewalkers. And that's Winky. And hello, could someone please let me back now? Winky's the Wesley Crusher character on if you're a Star Trek fan. All right. I sent this to one of my spacewalking friends when I got it. All right, this is a little video. We'll start in 1960. Very soon. Let's back up here. Let's make sure we'll get a running start here. The first spacecraft was launched in 1957. In fact, a few years ago, we had the 50th anniversary of launch of Sputnik 1. And I told everybody this is a great day. Today is the 50th anniversary of the beginning of space history. Because as soon as Sputnik 1 was released from its booster rocket, the booster rocket became a piece of space debris. So our industry started 50 years ago, plus now. So we'll start in 1960 with a few objects in Earth orbit. little spots or objects in Earth orbit. And we've got two views, far away and close. There's 1965, starting to get busy. Really starting to get busy in 1970. That's a lot of stuff. And then things got busier in 1975, 1980, 1985. These, by the way, are geosynchronous orbits. We'll have a chance to talk about that. 1990, that's about the time I came along, and things just got worse when I started doing space group. 2000, 2005, and this stops at 2010. Keep busy. Now, keep in mind, this is from a few days ago. It was in the paper. There's John Glenn at his 50th anniversary of launching into space. And when I went into space 50 years ago, there actually was space. But let's go back one to look at the current situation. Now, these are actually greater than 10 centimeter long and size. 10 centimeters is about 4 inches the size of this thing. The reason why that's a critical size is this is the size we can track. It turns out the United States and other countries maintain a pretty sophisticated network of very powerful radars and other instruments to look at what's in orbit around the Earth. They were originally designed to watch for incoming ICBMs during the Cold War. They used to be known as the NORAD network, and it's now called the Space Surveillance Network. If you think about it, it's important to know, something over the horizon, you want to know, is that an object in orbit, or is that an ICBM targeting one of your cities? It's a pretty important thing you want to know, right? Whether you start World War III or it's just another object on the horizon. So they spent most of their time tracking and cataloging things in objects. And the sizes they can see down to is about 10 centimeters from lowest orbit, this region here. And this represents a snapshot of those objects. Well, of course, each one's a big white spot, a little exaggerated size. But there's a lot of them. I believe the current count is somewhere around 30,000 objects that are tracked in orbit right now. And we'll get back to that in a minute. This ring is called the geosynchronous ring. Some of you are familiar with it. It's called the Clark orbit or the geosynchronous orbit. This is about 6 Earth radii, and the period of this orbit exactly matches the rotation rate of the Earth. And as a result, the satellite hangs over a position over the equator, and that's why your satellite dish doesn't need to track the same direction in the sky. And so this is actually a very valuable piece of real estate in space. It's a relatively small band, and it's got a lot of stuff in it. There's a lot of interest in this, even though the orbital rig problem out there is not acute yet. It's still a region of great interest. As you can see, the Leo regime is actually quite busy. By the way, these objects out here, we really can't see down to 10 centimeters, closer to 1 meter. So we can see that. All right. This is a question: where does all this stuff come from? Well, we've launched it into space. We being the spacefaring community. This is a graph of number of launches each year since 1957. And as you can see, there was the beginning of the space race. There was a ramp up in launches. Yeah. And then we got to about the mid-60s. We reached a plateau. And launch rates were relatively constant until the late 80s, early 90s. And then it dropped significantly. And it's come down quite a bit and sort of leveled off. What happened about here, about 1990? Anybody know? Cold War. At the end of the Cold War. A lot of these launches were Soviet military launches. And with the end of the Cold War, their launch rate dropped dramatically. Their spacecraft had very short lifetimes, 300 spacecraft, so the rate dropped dramatically. Another thing that's happened is there's a lot of bigger boosters that come online, so you need to, this is not quite the best metric because this only tells you the number of launches. We have a number of launches that can put up a lot of mass, so a little bit deceptive. But you can see it's gone down a bit and kind of leveled off the way. Now let's try another metric. This is the evolution of the catalog of satellite population. Again, the catalog in this case, there are objects that Space Command tracks, and there are objects that are cataloged. Now, track is anything that you can see today that you can find tomorrow and know where it is. Catalog means you've identified what it is, you've given it a name, a catalog number to know what it is. The rocket body from launch XYZ, you know, the spacecraft made by China or made by the United States or whatever. It actually has a name tag. And as a result, we can start talking about what things are made of. And so this kind of dark reddish curve is the total population. The blue is spacecraft, that would be the payload. Green is rocket bodies, that would be the thing that put it up there and was left in orbit. And the oranges are these mission-related, with brackets, shrouds, things like that. Of course, what's interesting is that since the early days of the space program, the population's been dominated by this red group, which is fragmentation, breakup. It turns out that if you put a spacecraft in orbit with an energy source, which is like you have fuel on your spacecraft, or you leave your rocket body in orbit with residual fuel on board. That is, as you know, rocket fuel, very powerful. That is a ticking time bomb. And it turns out maybe a week or a month or a year or a decade later, we've had rocket bodies explode. We've had a few spacecraft explode, but it's usually rocket bodies. And much of this, you see them go up, much of those jumps are from rocket body exploding. There's been more than 100 of them since the beginning of the space age. But you can actually see that actually the environment is dominated here by a series of events that started in 2007. This event and this event. In 2000, we'll talk about it in a minute. In 2007, the Chinese decided to do a little test. We'll test of an anti-satellite weapon. And no one told the people doing the test that you shouldn't intercept your satellite at high altitude where the debris will stay up there a long time. That's the debris change from that incident. In 2009, we had an accidental collision between a Russian satellite, we'll talk about this later, and an functioning iridium satellite, and this is the iridium cosmos position here, the big jump. Now what you'll see is these things go up and they come down. The up is the sudden breakup, you get a lot of people with debris. But typically in low Earth orbit, atmospheric drag brings them down over a period of time. So you see this gradual drawdown on the total population. But the net result is things are going up, up, up. And single event can have a huge effect. Again, this is just catalog. This is the tip of the iceberg. There's a lot of stuff smaller than that. Okay? It's distributed differently in altitude. This is altitude in kilometers. Excuse me, and like most people on NASA do everything in metric most of the time. The space station operates in this regime between about 350 and 400 kilometers. So as you can see, it actually operates in a very benign portion of the environment. This section of the environment, up around 800 to 1,000 kilometers, is very, very busy. There's a lot of stuff here. And then various different amounts and different altitudes where we've launched a lot of things. But it's not even distributed in altitude evenly. This is we call the UN figure 1 chart. It's a chart that we got in here. This is a composite chart, so don't read too closely. But the diameter here on the bottom is in centimeters. So this is about a meter. Here's 1 centimeter. Here's 1 millimeter, a tenth of a millimeter, 1/100th of a millimeter, 1,000th of a millimeter. This is 1 micrometer, right? This is right. Log scale. And this is actually a flux number, which is related to the number. But it's actually a number per meter squared per year, is our unit we typically use. And this is a cumulative number. So this is the number of a given size that would hit your spacecraft and larger. So it's a monotonic curve. It always goes up. But you pick a number, and this tells you everything that given amount of large. The reason why we did that is an object of a certain size can hurt you. Everything bigger than that can hurt you as well. So that's what we do with cumulative in that direction. A lot of people do cumulative. Down here, again, I said the 10 centimeters is what we can track to. That's this group. All of this is stuff we can't see. Now, when you get down to small objects, they're probably not a big risk. But there is a zone in here of stuff that's dangerous, nevertheless. And you can see we have a whole plethora of different instruments we use to measure. Just real quickly, the pink is a radar called Haystack, which is in Massachusetts that we use. These gold points are from the Goldstone data. The Goldstone dish in California we use occasionally for global debris. Most of the stuff down here is from return surfaces, where we count craters on return surfaces. But just to give you an idea that this is the population, as you change in size of the object, orders of magnitude, the population goes up even more or less. So, let's see. All right, this is the one I have to do with a different. This is a nice video, so we wanted to play this for you. Let's make it big. This is a fly through. Again, you can see the geosync in its ring. We're coming in from the pole. And as you get in closer, you'll see the object moving faster. And when you hold it faster, it's closer to the Earth. What's that? If you have a question, just tell me. We went up real formal here. So, you see, this is the geosync. By the way, the tilt is from old geosynchronous objects. They tend to have an odd tilt over time. So these are the ones that are active, these healthy ones are debris. This busy region out here is the GPS satellite region. So as you're getting close, we always call this the beehive. It looks like bees, angry bees, or in my yard, it's fire ants. But it looks like a, but you can see everything that seems, is pretty much, most of the debris is in this range. This is about 0 to 2,000 kilometers out. But you can see it's very, very busy. Also, if you look, the objects are going all different directions because they're on different orbital planes. It's not like everybody's moving together like in the movie. And nor is it all sitting still like it is in Wall. The mechanism that keeps them in orbit is their high velocity, and they continue with that velocity as long as they're in orbit. And it's like driving down, it would be like driving down the freeway with no lights. Everybody's going in different directions. Eventually, you're going to have problems. Fortunately, space is big. The collisions are rare, but they're not unknown.
And all these objects are moving orbital speed. Right?
Yes. So many of these are elliptic orbits. They're going a little faster than swinging out. So most of the stuff here is in near circular orbits from the solar environment. This is kind of interesting. Near the poles, it kind of looks like it's spinning around the effect of the height of the inclination. I don't know if it's near the poles. Okay. I like that video. It's fun to watch. You see a lot of things. The more you watch, the more you see. Okay, let's stop that. And we'll go back here. Okay, how do we know what's up there? Good question. We talked about that we can track things larger than 10 centimeters. In fact, the Department of Defense, what's called the J spot, the Joint Space Operations Center, really is in charge of things larger than 10 centimeters. They track them for us, well, they track them for everybody. They actually do collision avoidance. We'll talk a little bit about that. But NASA's sort of taken it on ourselves to take care of things smaller than 10 centimeters, primarily because the DoD is not sure what to do. As soon as you get smaller than 10 centimeters, it's very difficult to track objects. So instead, we try to do statistical measurement. We try to understand what's up there, where it comes from. It took us a long time to even convince the military that that was a useful thing to do, but I think they understand now that really it's just not their typical way. They want targets, they want to put the radar on. But the idea of sampling pieces of the environment and then trying to extrapolate what the whole environment is a little bit. For risk assessments, the DoD handles things larger than 10 centimeters by doing collision avoidance. And actually that's taken off in the last few years and is now provided, the service is provided to actually many foreign countries as well in collision avoidance warning. NASA takes care of the risk assessments less than 10 centimeters. We do modeling and trying to understand what the risk is and how to mitigate things. Mitigation is handled by NASA. We'll talk a little about mitigation. And our environmental projection is taken by NASA. We try and look at what's happening in the future. And this was arrived at over many years. The DoD didn't like us doing space debris. They thought they wanted to do space situational awareness. Over the years, in a give and take, we said, look, you guys are good at this, we're good at that, and over time, we want to cut each other. So it's actually a very good working relationship nowadays. Yes, here's a question.
So you earlier mentioned about the atmospheric drag.
Mm-hmm.
Right? I don't know how it works in introducing the debris.
Okay. Of course, the atmosphere is very, very thin at it's non-resistant. It turns out that if we were to shut off, if we were to abandon the space station right now, at about 350, 400 kilometers, atmospheric drag would bring it in a few years, I think 3 years. What happens is these particles, atmospheric particles in the atmosphere, hitting the front at all times. It's plowing through the atmosphere. And it's just like you stick your hand out the window in the car, you can feel the air drag. It's a little better than that. I think the force on the space station is like a nuke at all times. That's how much atmosphere is that. And that added up over months, and we will eventually drag it down. So small debris are more susceptible. Just like if you drop a feather, it goes a little slower. The lighter an object is for its size, called its ballistic coefficient, the quicker it comes down. And so it's a matter of, but it's also a function of altitude, because the atmosphere drops off exponentially with altitude. So a typical spacecraft at station altitude lifetime is months to years. A typical spacecraft at Hubble altitude is lifetime is decades. A typical spacecraft at that 800 to 1,000 kilometer range is centuries. And the debris comes down, like I said, faster because it tends to be smaller. becoming a very small debris. But we, as you can see from the graph, we're creating debris faster than it's being removed by the sun. We're also launching mass into orbit faster than it's being removed by natural causes. So you don't have to do complex modeling. You know, if you keep putting more and more stuff into a finite space, you're eventually going to start having problems. So the atmospheric drag it's just it's, for lack of a better word, friction. It's a dissipated force that's using up the energy, slowing it down and causing the orbit to decay. There's one other interesting effect. The sun has an 11-year cycle in the radiation, in the extreme ultraviolet radiation that causes the atmosphere to expand and contract. Right now, the atmosphere, we're moving toward the solar vacuum. The atmosphere is actually getting denser, expanding, breathing, and so everything's dragging out a little faster right now. And the space station has to adjust its orbit accordingly. It's not a very strong solar maximum, so it won't be a very strong effect on the debris. But if you look at later when I show some models, you'll see there's periodicity, above the periodicity. Does that make sense? But basically, it's a dissipated force that's always working. It's like friction. It's always working in the opposite direction you want to go. Yes, except stuff at low altitude. When the astronauts drop a tool or a piece of something, it's like some typically so relatively fast there. But again, it's a function of altitude and how fluffy the altitude is.
Is that because of ballistic coefficient?
Yes, it is. Okay, here's back to our data sources. Again, down to 10 centimeters is the space surveillance network array of giant radars. NASA has used what are DoD assets in non-DoD ways, what's called the Haystack radar and the HAX radar, and these are two radars in Massachusetts that images. Haystack can actually see objects down smaller than 5 millimeters in 1,000 kilometers. That's a pretty impressive radar, but it can't track. So we do is we stare and count objects, and from that are able to understand statistically what's happening in the environment. Goldstone handles this range below 1 centimeter, although we only use it limited and it has a lot of issues with it. For smaller sizes, we're essentially left with satellite space. The spacecraft inspections, which we used to have all the time, but now the shuttle's no longer flying, we don't have quite as many. So the question is, all right, well, this is what we can see. Well, what's important? Well, this is an old chart from the space shuttle, but the space shuttle would have major cargo bay damage if it got hit by a 1 centimeter object. 1 centimeter is the size of a Tylenol tablet. Very small object. If the RCC, which is the leading edge of the wing on the shuttle, were hit by a 1 millimeter object, you would have penetration and possibly failure on the wing. An EVA suit is vulnerable to objects about 0.2 millimeters in size. Very, very small. But the risk is always a function of two things: how big you are and how long you're out there. And a human being in space is relatively small, and he's only out for, he or she is only out for 8 hours or so. So we call it the area time problem. It's a little bit like radiation exposure. The longer you're exposed to radiation, the more statistically you're in danger. So if you minimize your exposure time or your exposure area, you minimize the risk. When it's actually, when the shuttle's released to fly in a mode that minimizes the risk. The other thing is there are areas of your spacecraft that are more sensitive. It turns out, I think the region on the spaceship that's most vulnerable is the back of the hand of all things. It's very, very thin. So penetration there could easily have caused a leak in the suit. But again, the back of the hand is relatively small, and they're only out for a few hours. So, but this kind of gives you some idea of what is the danger zone. I will say that 1 centimeter is the size that the space station is shielded to, the shielding. Most spacecraft would take major damage from 1 centimeter object. Yes?
That chart's for singular events. What about erosion, where you get smaller things that over time can build up and cause damage?
Yeah, typically, and I'll show some examples later, typically they're little onesie-twosie events. And I've got some pictures from Hubble and stuff that hopefully will answer that. And people thought there would be a problem like erosion, like eating away at things. But it turns out that that's really not a problem, at least not that I've seen. Maybe with optical surfaces it might be a problem. But typically for spacecraft, that's not a problem. I'm going to show you some pictures right now of actual damage on this is Hubble Space Telescope. To give you some idea, there's an astronaut right there on the end of it. This is actually the first servicing mission. And one of the cameras got this picture of one of the main dishes here. And it actually has a rather large hole in it. And ground tests that we did here on Earth with Hubble Impact suggest that this material has the Bugs Bunny effect. Remember Bugs Bunny would run through the wall and you see the outline of his ears and everything? That, in fact, this is the size and shape of the object that went through that dish. Now, we're not for sure for positive, but detected anything else. One thing I failed to mention was the velocity of the spacecraft going orbiting objects going very, very fast. In low Earth orbit, the speed is 7 or 8 kilometers per second. If you're going 7 kilometers per second this way, and then if you're going 7 or 8 kilometers per second this way, you can get upwards of 15 kilometers per second impact. To put that in context, the bullet is around 1 kilometer. And of course, you guys remember from physics, energy goes to the square of the velocity. So 10 kilometers per second relative velocity is 100 times the energy. Another way to think of it is the kinetic. If you took your projectile and made it out of a material that had energy in it, like TNT or C4 explosive, some kind of chemical explosive with a lot of energy, what velocity would you have to get to until the kinetic energy equals the chemical energy inside that object? And it's about 1 kilometer per second, give or take. So in other words, once you get above 1 or 2 kilometers per second, there's more kinetic energy in that object than any possible chemical energy that's inside of it. And in fact, that's why actually ICBMs are actually not very good weapons, except when you carry nuclear or some sort of gas or something. Carrying conventional explosion conventional explosive in an ICBM is actually counterproductive. There's more energy in the kinetic energy of the rocket than in the payload of the explosive. So we're talking about very, very high energy. And I had an argument with one because you mean to tell me that if your spacecraft was hit by a marshmallow, it would do one thing? Yes, it would. It's fine. So it doesn't. At those speeds, it no longer material type no longer is important. It's the energy, the kinetic energy of the material. This is an example of the photography of the Hubble from 7 years in space, and all these little marks are impacts on the surface of the Hubble. So as you can see, there is damage. It's not so much erosion as pop marks all over. It's like you've been driving behind those big trucks on the freeway here. Here's an example of a blown up one. You can see the crater on it. But I've got more to come.
Is that a lumen travel?
I think so. Some of this actually has a kind of blanket, of mylar blanket. If you recall, some of the original solar panels had some problems, so they were replaced, and they actually brought back some. And my colleagues in Europe were able, since they built them, they were able to analyze them. There were a number of these holes in the Hubble solar array. In many cases, it turned out it was difficult to do the chemical analysis on these because the arrays themselves are rather complex structures, but you can see the holes there. Unfortunately, there's no size on them. There's a size. These are relatively small. This is 1 micron here, so it's relatively small impact. There are many. This was 1 millimeter. So this was a several millimeter size hole in the solar array. All right. This is a picture of this section here. It's called the WISPIC 2 camera. The last Hubble servicing flight removed the WISPIC 2 camera and replaced it with the WISPIC 3. That's the wide field planetary camera. It's one of the pictures. But it was WISPIC 1, this is WISPIC 2. And if you look carefully in this picture, this is actually a photograph from on orbit. You may be able to see that we have impact. I wasn't sure if it would show up on this one here. Can you see those? That's kind of hard to see. It turns out we have one there. It turns out we have about 300 large impacts, large being big enough to be easily measured. And this is a witness plate to the flux environment of large objects. These are hundreds of microns objects. Well, they have large. But we're in the process of analyzing this right now. We had some problems because the HS people really wanted this instrument to go to Smithsonian. And we really wanted these impacts to understand whether they're micrometeoroids or orbital debris. So it took us a long time to convince them that this was a good thing. And I actually talked to one of them and said, look, when you put this in the Smithsonian, you'll have these cheese, we're cutting out these holes, with cheese holes. So what you should do is have you exhibit a little magnifying glass. Look at these impacts. That makes it part of the whole picture. If you go to the Smithsonian and see little magnets, you'll know what.
So those are actually dents, they're not really penetration.
They're not penetrators, they're actually craters. They actually look like craters on the moon. And I've got some examples here. Let's see if we got. I don't have examples of these craters, but here's some. I'll show you in a moment. These are some cell impacts. This one from a window. This is one from the radiator. The radiators, we got a lot of large impacts on the radiators. That's the radiators, the big aluminum radiators inside the wings of the shuttle. I mean, inside the doors of the shuttle that help cool the electronics. This is a ding on a radiator. I'll go through these quickly. This is the damage it caused. We recognized radiators for a long time as not a crew risk necessarily, but a mission risk. It turns out that early in the shuttle program, if this one had hit here and broken this radiator line, which had ammonia in it, it would have caused one of the two radiator lines to leak, and it would have caused immediate intermission for the shuttle because they would have to close out and come off this on the cool. But I think as time went on, they armored these with extra material here, and they did some other things to try and make it a little more robust. But this is a problem if you're ever in spacecraft with any coolant material. You've got to run liquid through cooling radiators. You're susceptible to micrometeoroids and orbital debris. So it takes the nick in one of these, and you can leak your coolant. Here's a crater. You see how this one actually is a penetration, actually. Oh, that's a big one. That was a several millimeter object made that one. One of the things we can do is we can do chemical analysis. I'll show you some craters in a minute. But we can do chemical analysis of one thing. First of all, we put them in the electron microscope, and we can tell if it's orbital debris meteorites, and they're about half and half from the windows. Of the orbital debris, we can look, well, what's it made of? Well, a lot of it is aluminum. Spacecraft manufacturers like to make spacecraft out of aluminum. It's a nice, strong, light metal. A lot of it, strangely enough, these little bitty guys, paint. And that's because you guys have painted houses before. I'm sure you had a house that's been out in the hot sun for a couple of years. What happens to the paint? It flakes off. It's much worse than space. Paint flakes traveling at orbital velocities will make a big ding in the window. So this turns out to be a problem for windows and things, not so much a problem for bigger objects. This is just a nuisance factor. It would be dangerous for a person on an EDA. But a small fragment of it is stainless steel iron. Problem with this density is so much higher than aluminum. An equivalent size object in steel can do a whole lot more damage because it's massive. So in other words, if a 1 centimeter object would penetrate your shield with aluminum, it would take only a fraction of that of steel to penetrate. Just quickly, this is what my colleague was going to talk about. A lot of what we do is actually modeling spacecraft, and this is some early designs. It may actually be Mir, I don't remember, but I just pulled one of the shows. I know what I said. These color codings are different regions on the spacecraft where we're hoping to put shielding, or in this case we're designing shielding. Because the orbital debris environment doesn't just come from one direction. It comes from certain directions at certain velocities. Basically, most of the debris, if I'm a spacecraft, I'm going around the Earth, and that's the Earth's surface that I'm getting to. This is the direction I'm traveling around the Earth. Most of the debris comes in a flat plane like this. Think about it. And most of it comes from frontier flux. You do get some flux from the back, but it tends to be slow velocity. So the shields you design for slow velocity is different than the shields you design for high velocity. So it turns out you can custom design your shield at different parts of the spacecraft to shield different types of orbital debris. So a lot of the color coding is the different kinds of shields. So what we actually do is we make a model of the spacecraft. We fly it through the environment. This is called the igloo. This part is meteoroid, and this part here is the orbital debris. We have equations based on gun tech of what speeds and what angles will penetrate what kind of shield. You design shields, and then you work out what the risk is. And this is how the space station was designed. The space station was designed. What can we do? Because shielding costs weight, and weight is money, and any shielding you put up means that's one less something else. So there's a constant struggle about shielding and how much we could do. But the idea was to limit the overall risk of the station to a reasonable number. And the original design environment was, I believe, 95% of no penetration for 10 years. Now, we've already been up for more than 10 years, so far so good. But there's always the risk of getting hit by a piece of space debris. The shuttle, it turns out, had some very sensitive areas, the leading edge of the wing and the nose. The color coding tells you the sensitivity of what different size crater would cause failure on the entry. And the most sensitive area are these areas right here where Columbia was hit by not from space debris, but from the tank debris. But we've known for a long time that these regions of that particular spacecraft were more sensitive.
Well, like you said, even though the foam was very lightweight, in fact,
Well, it was only going a few hundred miles an hour.
I'm sorry?
It was only going a few hundred miles an hour.
It didn't actually.
I remember right after Columbia, I came in to help with some of the investigation, literally the next day. And someone had a piece of the foam, and I picked it up, and I said, that's the closest thing to nothing I ever felt.
Yeah.
It was so light. It's like, what's this? And it turned out it was the foam. I would have never in a million years thought of that. Now, orbital velocities, I would have believed it, but not a few hundred miles an hour. Okay, we've had the space station up for a while. Let's see what orbital debris things we found on the space station. This is that there's damage on the solar panels where a piece of debris went through. We've done photographic survey. This is a window on the Zvezda module. Very much similar to the kind of stuff that on the cars when the gravel trucks and stuff. It's another large window. You can't replace it with space, so these are big issues. The shuttle used to come down, we'd have dings, we'd replace the window. That's easy. This is actually an impact seen during an EVA on one of the Russian modules. Actually went through the outer insulation layers there, thermal blanket. Let's see, particle estimated 2 to 3 millimeters in diameter, penetrated the module's thermal blanket and the underlying steel mesh, fiberglass, and aluminum honeycomb layers, but did not damage the compressor immediately below. This is one of my favorites here. This is an astronaut on the spacewalk. Right here, impact, it's blown up here. You can see it looks like a crater on the end. You know? The astronaut can't here. It's quite small, but it's very nice crater. It actually, the physics that creates craters on the moon is very similar to impact cratering physics on micrometeoroid orbital debris impacts. Here's some more. This my colleague Stan Love. I was actually listening to his spacewalk. Stan's a scientist. Most of the astronauts are not scientists. He got a space scientist. And he actually got a PhD looking at the LDES spacecraft, counting the craters on the LDES spacecraft. So he and Rex were all hanging around the spacewalk, and they were done. And he was moving back in. He said, "I'm just going to wait here." And he's ready to go back. And I'm going to look at the side. So Rex was finishing up, and he looked down. And he said, "Hey, there's a meteor crater right here. There's an orbital debris crater right here." And I thought, of all the astronauts, they picked the one that was most trained on finding craters. But he actually found it on this handle around the airlock. And they were having problems. The astronauts were coming back and cosmonauts coming back with their gloves torn, which really worried the folks on the ground. It turned out it was from that one impact. It's the metal, sharp metal, and they were cutting their gloves. So I think they put some tape on it or something to avoid that spot. But no one thought about this being a risk. I mean, you get a little ding, a big deal. So, I mean, an astronaut out there on a spacewalk and carrying the gloves is a big deal. So, again, they didn't let it fly after that. No, I'm just kidding. Here's an example where it went through an EVA. Let's see. Yeah, it was an EVA tool stored externally on the ISS. So you can see it actually went through that section. And there is one of the MPLM logistics modules. Actually was only up for a few days and came back with a nice hole in it there. Nice round hole. Again, we talked about shielding. The strategy on it turns out you have to work really, really hard to make a spacecraft like the ISS shielded against 1 centimeter line. You have to work really, really hard. So we can only track the system. So everything we can track, we can maneuver. So we can hear them and maneuver against it. So the difference in the number of objects we can track against to the number of objects we cannot shield against, that gap, is about 10 to 1. In other words, for every object we dodge, there are 9 objects we don't see. So that's the residual risk. So we're always trying to do this. The shielding guys are trying to push down. So shielding guys are trying to push up the size of the shield tube, and the measurement guys are always trying to do. So maybe in the near future we'll close that gap. So we'll see the space flight will be more safe. But it's not a trivial matter either way. And this is this is one of Russell's charts. Real quickly, I want to point out that it turns out that I was thinking about bringing the props, but I forgot. You can go online and look at this. But if you shoot a hypervelocity target traveling, one of the things about hypervelocity with high speed, you're actually traveling faster than the sound speed of the material. So the material properties are no longer important. It makes everything acts like a liquid, so to speak. Not until it's slowed down do material properties like strength of the material start to work. So what they found is you don't want to make shielding thicker and thicker and thicker as you speed. You layer it and you separate it. The idea being it comes through an initial shield which spreads out and slows down the debris slow enough so that the Kevlar can catch it. You just put Kevlar on the outside, it'll punch right through. But if you put multiple layers and separate those layers, you can shield a lot better. So just a case out of the whole science of how you build shields. And of course, we actually test these out of light things. We have guns that can shoot up to 7 kilometers a second and actually test the shielding too. And we have computer programs to try and project that out as fast as below. I haven't mentioned meteoroids. They can travel upwards to 70 kilometers.
It sounds like the shield doesn't actually stop the object. It kind of slows it down to where it's no longer dangerous.
It slows it down and spreads it out. So there's examples where it goes to the whole, in the back, it looks like a shotgun blast, but you turn around and have it gone through the back shield. Yeah, you're actually doing different things. You're actually breaking it up and slowing it down. And then these stuff shields that they discovered, and they spent a lot of time doing these Kevlars and Nextels and things. And then one day someone came and said, have you tried fiberglass? And I said, well, we haven't tried fiberglass. Well, could you try it? And we found out it worked just as well as it does. But it would have been cheaper and lighter, but you do what you think is the best thing. All right. Collision avoidance maneuvers. We talked about that. There have been 15 such since 1999. 3 times each day, the JSPOC, tracking all the objects in Earth orbit so that they can see, do conjunction assessments out in the future. They project for it and look for close approaches. They actually do some pretty sophisticated statistics. But in 2011, there were 2 collision avoidance, but in January of 2012, we had 2 more. But if you look, one of them was from a debris from a Cyclone rocket body, Russian rocket body, but the others were from our Kuiper red ghost, which is a significant contributor to the orbital debris.
What's the size threshold that triggers the collision avoidance?
Anything they can see is dangerous. In fact, we keep getting this from the MOD folks. Well, how big is that thing? If you can see it, it's dangerous. The shields can't stop it. So 10 centimeters enlarged is what they can see. And 10 centimeter is a catastrophic collision.
How do you deal with that amount of debris that's naturally occurring to your object?
Well, it turns out that if you go back to my chart, remember the chart I showed was from the population. It turns out at right at 1 centimeter they diverge. So the natural stuff goes down, the man-made stuff plateaus. And so once you get above 1 centimeter, the environment is dominated at this altitude by man-made stuff. There is big natural stuff, but it's on deep down on that power law curve. So every once in a while, the Earth encounters a 10-meter asteroid. We've got lots of 10-meter stuff in Earth orbit. Now, 10-meter asteroids travel quickly and so forth, but below about 1 centimeter, they're approximately the same order of magnitude in terms of contributors. But above 1 centimeter, it's dominated, at least in low Earth orbit, it's dominated by man-made stuff. All right, I didn't know how, I'm going to make a sudden break here about a whole other aspect of orbital debris. So I put the obligatory change to the pace chart here. What happens when those big things come down? This is a whole other question, right? In the last 6 months, we've had 3 big reentries, 3, I could say, high-profile reentries. The first was UR, the Upper Atmosphere Research Satellite, which is an American NASA satellite, actually the largest NASA satellite to come down to the skyline, come down uncontrolled. Then, hot on its tail, was a German astronomy satellite called Rosat. And then, hot on its tail, was the Russian Spacecraft, which failed in Earth orbit with a very large tank of hydrogen. In fact, we got pulled into very high-level discussions concerned that these tanks full of hydrogen. Fortunately, after much work, it looked like that these tanks resistant in aluminum would fail to disintegrate and spill the contents of out. You recall the USA 9193 event, which occurred in 2008. Problem one is with frozen hydrogen and titanium, and high confidence that it is going to survive in the ground, still full of hydrogen. The hydrogen is nasty stuff. The concern was that that tank would fall in some little town in Kenya or India. All the townsfolk would come, somewhere for the community, they don't know, the communication's not so good. All the townspeople come up to what it was, the gas pipe was born, so there was a lot of concern about that. We were pretty sure that the total strength was not really a problem. We ended up falling over the ocean. So, all right, so a little bit about reentry. Three really big reentries. Two of them, in a sense, planned, one not planned. Oh, I got to put this. Here we go. So right after all this stuff with UART happened, here comes Bruce the Rocket. And this is Agent Ed. Okay, so he's like the man in life. The NASA said the dead satellite will crash to Earth, and the odds that it will hit anyone are minuscule. I just hope the news media doesn't overplay this. And it's got the news media, it's got the hard hat. He goes, next, the satellite falling to Earth, why you are probably doomed. And I had to be the NASA guy with the media for the whole UART thing. They ask crazy questions. This is my favorite thing. Yes, the satellite is falling to Earth, but it will break up into debris. And everybody says, that's debris. And don't worry, most of that will burn up as it enters the atmosphere. Flaming debris. It is true that most things burn up, but not everything burns up. It turns out that certain materials will make spacecraft out of tend to survive reentry, and certain spacecraft do not. Aluminum usually burns up in the atmosphere. It has a relatively low melting temperature that is discovered by chemistry class. But titanium is a very common spacecraft material and a very high melting temperature, so it tends to survive. Typically, an object re-enters some 10 to 20% of the mass survives to reach the ground. So here's some examples of objects that have reached the ground. In Texas in 1997, this was an upper stage of a Delta spacecraft that fell in two different places, in Georgetown and somewhere else. This is a large tank, a titanium tank, and this is a large steel tank from the Delta upper stage. The same kind of spacecraft fell over South Africa, the same kind of rocket in 2000. They found this piece, we never found this piece. Here's a solid rocket motor from a Saudi Arabia fall in 2001. Here's some pieces that fell in Guatemala in 2003. That's a composite overlap. And here's an object that fell in Argentina in 2001. So as you can see, it's international event.
How much was Cosmos 954?
Oh, the one that fell over Canada? Actually, it's a pretty good sized spacecraft, but it mostly disintegrated. That was the problem. It was a Russian spacecraft with a nuclear power plant. And 80? I think so. It's actually a pretty good sized spacecraft, even though it's physical size. The problem was, as it disintegrated, the nuclear plant, it just spread nuclear material all over. That wasn't so much a physical impact. Yeah, that one was one that viewed around. There was a big cleanup that was there. Fortunately, it's easy to find the pieces. You go out there. I never looked closely at that. I should look at the how many pieces and stuff to count. How I have not worried too much about it. It turns out that we usually don't get really worried about spacecraft unless A, they're very large, or B, have toxic material. So a nuclear reactor coming in, people get worried about. A large UR-600 spacecraft, people get worried about. But there are things up there that will eventually come in that are quite large. So the question is, it's the old thing, whatever goes up must come down. What's the biggest thing up there? ISS. ISS, we're starting right now on the plan to eventually deorbit the ISS. It turns out it's a non-trivial process. You recall Mir did that about 10 years ago. And again, it was a non-trivial process. Their idea is to drop that thing over the ocean where there's nobody underneath the footprint. And it turns out to be hard to do. It's not impossible, but it's very challenging. One of the things we do is try to model material of how they'll survive. How many pieces will survive? How big will they be? How much mass will they be? So one of the things we try to do is whenever we get a chance, try to calibrate on those. When the Jules Verne ATV service vehicle was deorbited over the ocean, we had a couple of planes up there and they measured it, and that's in the video. I have yet to see a re-entry like this. They're spectacular. That's a pretty thing going across there. One of the things that I've done is I put together some tools trying to understand what is the risk of people on the ground. It turns out some very smart folks at Columbia University put together what's called the global gridded population of the world. They've now updated this. There's a whole series of these. You can download them off the internet. They're gridded 5 arc minutes by 5 arc minute squares on the Earth to tell you approximately how many people are in each square. From that, you can make a digital map of the population on the Earth. From that, we can then fly different re-entry scenarios to see what the risk of people on the ground is. As you can see, where people are concentrated. There's none of the people in the Ganges River Valley. In northern China, there's Rio, Mexico City, the northeast coast of the U.S., northern Europe, England, and there are other regions with very low density. The Sahara, the Outback, the tundra. So it's a very useful piece of information for all kinds of things. Actually, when we first started using this, we wanted to project out into the future because we were planning spacecraft. We want to know what the population is going to be like 10, 20, 30 years out. And so we contacted the folks at Columbia and they said, well, we don't really have it. So we went and got the data from the UN, country by country, and adjusted those projections. And then we told the guys at Columbia, they said, hey, that's a great idea. So they went and did it after we did it. So we were actually helping them a little bit. This is some work that I did. This is actually the inclination of the spacecraft. And this tells you the approximate density, average density underneath the footprint of that spacecraft as a function of the orbital tilt. And as you can see, if you're about 30 degrees, you actually have more people per square kilometer than if you don't have a polar orbit. The polar orbit is lots of the time until the north and south pole is not a whole lot. But the variation is about a factor of 2. This is 2000, this is 2050. You see the increase in population. So this is the tool we use to figure out what pieces will survive and then what's the risk to people on the ground. Our goal is to design spacecraft in such a way that the risk on the ground is 1 in 10,000. Someone somewhere will get hurt. Oh, got to have another card. If your satellite crashes to Earth, this is right after the USA 193. If your satellite crashes to Earth, it'll build a toxic field. Does it have a self-destruct mechanism? Huh? Something that will make the satellite break apart. Oh, sure. Well, what is it? The ground. This is a chart I put together for USA 103 work that we did originally. This is a little bit different way of thinking about it. If you have a spacecraft with a toxic material on it, what is the probability that will fall in place in a certain density or larger? So, this is the population density, number of people per kilometer square, and I've marked very places. So a very dense place would be Manhattan or Hong Kong. And this is the probability on a log scale from 1 down to very small that it will land in a place of that density. So you see the odds of the spacecraft, maybe there's inclinations. It turns out it's not only weakly inclination dependent. It turns out the probability of landing in a place as dense as Manhattan is relatively low. But the probability of landing in a place as dense as Vatican City maybe as high as 0.1%. Or the country of Liechtenstein, you're not talking about several percent. So this, if you do have a toxic material, these numbers are the kinds that make people worry. Because Liechtenstein is not, Siberia, it's not Mongolia, which has a very low density. It's a relatively high density of folks. So this is the kind of tool that you can use to kind of make those assessments. One more thing that was, this is something that worked I did just a few months ago. The question came up, what's the probability that the spacecraft will land in the ocean? And as you know, the Earth land speeds are not evenly distributed around the Earth. And in fact, the Earth is about 3/4 ocean and about 1/4 land. So I came up with this plot. So what is the probability of the satellite avoiding land, landing on the ocean? The red is for a single impact point. And you can see if you're near the equator, you actually have a slightly higher chance of landing in the ocean than if you're near the poles. And it's about 3/4 like you would expect. However, a lot of this at these high polar orbits is from Antarctica. So I've got an Antarctica here. If you take Antarctica out, if you consider Antarctica an ocean, then the numbers are much more like the ocean. But then my boss asked the second question. He said, well, objects don't fall in a single place. They tend to have a footprint of debris, screw field. So I did an 800-kilometer footprint, which is sort of a typical screw field. And I said, what is the probability that entire debris footprint will be over ocean? And that drops it down to more like 60%. And again, you see this phenomenon with Antarctica. But this is a little more complex. It actually had to do with the geometry of the footprint and the shape of the continent. So it took a little longer than the computer. But this is the kind of things you can do with the kind of data. By the way, we have a publication you can look at. You can actually sign up for. It's free, called the Orbital Debris Quarterly News. You go to the NASA Orbital Debris website. You can, and they'll send you the announcement on it. And I'll have this chart in the next show. This is my article in the next Orbital Debris Quarterly News. All right. We talked about stuff that's in orbit. We talked about stuff that falls from orbit. The question is, what is the future? That's one of the other things we look at. What's happening in the future? We have a number of models which try to simulate what's happening in the future. As you know, anything with future projection, you always have to take it with a grain of salt. However, it's a very powerful tool for figuring out if I do A, if I do B, how does that affect the world? What is the global picture? Of course, one of the things you have to worry about is what's future launch traffic. You saw that launch traffic dropped after the Cold War significantly. And before that, before 1990, we had projected high launch rates out into the future and had to readjust. But I said, well, let's stop that. Let's just make an assumption that today, all launching stops. It's obviously an unrealistic assumption, but we stop all launching. Everybody shuts down their space program. What happens to the debris? And it turns out that what dominates the long-term environment is collision. Stuff that's already happening. Big things hitting big things. So, the blue is impact object. The green is explosion fragment. And we start here, I think in the year 2008, I think is where we stop everything. No more launches. And so you see these two start to decay. Atmospheric drag gradually brings down the numbers. And it gets slower and slower and slower. We're out here 200 years. We're down to about half of what it is. But what happens in the meantime is collisions start occurring. And collision debris starts to grow. See, that this is the 11-year cycle I was talking about. So what happens is, even if we stop launching today, the environment gets worse over time. This is what's called the Kessler syndrome. Don Kessler was my first boss, the inventor of space debris studies. And he realized that if you get enough stuff up there, you basically have a runaway reaction. The time scale on this is centuries. But what this says is that in certain regimes, we're already at that point. That the amount of material up there, collisions will create more material than is removed by atmospheric drag out on a 200-year time scale. What this says is, if we want to preserve the future environment, we can't just do it passively. We have to do it actively. We're really serious about keeping the environment from getting worse. And if you add in launch traffic, all occurs. See that? This is, remember, is if you stop launching today. Collisions have already started happening. In 1991, a Russian non-operational spacecraft was struck by debris from the Meteor Crater spacecraft. In 1996, the French Cerise spacecraft had its boom, as a military satellite, had its boom severed by a piece of French launch rocket debris. I talked to a logger. He was so disappointed that he wanted to take that case to two different countries because it was in all French. The French took care of it internally. The whole issue of liability. In 2005, the U.S. derelict rocket body was struck by a fragment of Chinese launch vehicle debris. But the big events, of course, as we mentioned, this is one of my videos. Just to give you an idea, this is actually a relatively low velocity impact. The large impactor, a ball sphere, this is about 2 kilometers per second, so relatively small, into a composite space. It's not a real spacecraft, but it's made of real spacecraft material. It's a CubeSat. So, you know it's good science when things blow up, right? All right, here we go. Here comes the ball coming from the right. Can you see it there? So here it comes. Can you see it? All right, there it is. And this, of course, is in slow motion. And like I said, this is actually sub-hypervelocity. This is more like typical speed, similar to what you would find in artillery ranges or something like that. Needless to say, it does a lot of damage to the spacecraft. The reason why we do... You want to show it again? Okay. Like I said, coming from the right, there's a hole.
Cannonball.
Cannonball, yeah. And you can see the shock wave going through the building. Now, if we did this at hypervelocity, we would do more. But one of the things we were studying was relatively low velocities versus hypervelocities, with the size distribution of debris probably similar. Plus, we were using material that's more like people are using doing spacecraft nowadays. Actually, it's not irrelevant, believe it or not. Typically, we do spheres because you don't have to worry about their orientation. But tests have been done with rods and with plates. And it turns out something that's that big, it wouldn't matter. But when you're talking about designing shields, it turns out the shape of the debris is important and how it hits. And it's sometimes counterintuitive. What you think would penetrate may not, like the sphere, and then some other orientation will. And when you get this large, it's just going to destroy the whole thing. The reason why we did these tests, we're counting pieces. We wanted them in size distribution, and we could get them.
My question is there a chance that the parts obtained after explosion can collide with each other again?
Yes.
Because if you use as you consider the law for a moment of conservation, there is an explosion that the particles move the whole stack. It's like it will collide again after taking the revolution.
Hold that thought. I'll show you a video in a minute. We'll talk about that. Hold that thought. Yeah. Eat my straightener. Just give you an idea. We count the pieces from these breakups so we understand the breakup system. Because the power laws describe the number of pieces, the distribution, the size, and material. Okay. But let's see. Just real quick, this is the Fengyang 1C breakup where the Chinese did the deliberate anti-satellite test. This is what happened to the catalog population. The blue is from January 2007. The red is January 2008. The green are the particles from the Chinese collision. So you can see in certain regions it's doubled. One event did that. Okay, and then we have the 2009 collision between the Iridium spacecraft and the Russian dead Cosmos 2251. The reason why I said that is watch this video. This is a video, computer simulation of that collision. And you should be able to see. Okay, we got the red object's the Russian, of course, and the green is the U.S. They're about to hit. They're orbiting the Earth. And they hit. This is the geometry of the collision. Bang. What happens in this collision, strangely enough, is there's very little momentum shift between the two. You basically get two independent explosions. So they pass through each other. It turns out they probably don't collide very much because of the large amount of space. But in a very short amount of time, in a few revolutions, it's sign down in the lower right. They basically completely wind around the Earth. They look like a banana. So within a few hours, we're already looking like this.
When they cross, do they create more debris?
Well, it turns out that the probability of recollision is there might be an occasional recollision, but they do these cross points they call pinch points where they actually come together, but in percent over time. But it seems like the odds of them, because space is so big, the odds of them recolliding in a short time is relatively small. Now, over the long run, yes, you can get clear. The big problem is when you get small things, it's big things that are already resident space objects that are already there. See, now it's just a continuous spin particle. This is just a few days later. Okay.
What causes them to go out in all directions? After a while, they'll all...
I'm sorry, to spread out?
Yeah. Don't they all just spread out over...
Well, first of all, there's a little bit of delta velocity that causes the cloud to expand. We follow the origin stuff of the cloud. And that's just from the shockwave through the material giving different velocities. But what happens is each one has a slightly different orbital period, and that stretches it out. And so pretty soon, the snake catches its tail, and they start wrapping around. Basically, if you watch closely, it actually looks like a spiral for a while. But then after a while, you basically get like a planetary ring. And that's a very similar phenomenon that forms a planetary ring. The next video will show you what happens in the long run over a period of about a year to the orbit plane. And this time, the individual objects are not a point. Now the individual object is a ring, okay? And you'll see how the rings process the time. It turns out the Earth is not quite a sphere. It actually has a bulge around the center like some is. And as a result, the orbits precess as a function of their tilt. So you'll see this in the, and because each object has a slightly different orbit, they will precess at different rates. So you'll see that. All right. this one works. So we have the collision. And watch on the lower right, we're talking about July, August, September, October of 2001. So going over a period of months. So not only do they quickly turn into a ring, but before too long they completely grow. And the red is going faster because that's the Russian debris is actually at a different inclination than the American debris, a higher inclination is perceptible. But you can see this is 2000, we're not even up to this window today. That's what it looks like. Makes it look like a ball. So your question is, what happens is each one explodes, and it has to behave like two separate clocks, separate debris clocks. And it's true that the orbits were intersect, but we've never seen any collision between them. They might happen, it certainly could happen. The biggest problem is, again, this debris will still be orbiting the Earth much of it 100 years from now. And there's a lot of stuff up there. Eventually, I guarantee you one of these pieces is going to strike. And whether it cause another catastrophic collision, then we do. It has to be big enough. It has to be big enough object to strike the big enough object to create like more debris, to create like more debris. But that's the Kessler syndrome. Debris, objects hitting each other, causing more debris, which then causes more collisions, which then causes more debris. It's similar to what happens with nuclear fission. That's on a much longer time scale. Iridium collision. The phone lit up. I had to talk to the press. One guy called me from Nature News. The guy from Nature News wanted to know about the upcoming Hubble return. Well, we're looking at this very, very closely. We're trying to get our understanding of what's happening in Nature. So he quotes the next day. NASA says they may cancel Hubble repair mission. Well, someone in Senator McCulsey's office, Senator McCulsey is a powerful senator from Maryland, called NASA. What's this about you canceling the Hubble repair mission? We're not canceling the Hubble repair mission. What are you talking about? And so, first of all, he finally got back to me. My first impression was, wow, Senator McCulsey's people read Nature News? No, I didn't pick up my wires. So when they called me, I was like, what are you talking about? And so fortunately, I didn't get in trouble because the people who make high decisions over the NASA very well know the phenomenon being misquoted by the press. So once I explained that's not what I said, no more problem. But anyway, you got to be careful when you talk to them. After this, we had press training. So, but you know you've really made it when you make the weekly reader. I get a call from a friend of mine from high school. She said she was passing out the weekly reader to the second grade students, and she said, "Oh, look, it's about space junk. I have a friend that studies space junk." And I'm like, so I tell the kid, I show this to them. I talk to students, and you know you've made it when you're in the weekly reader. And one more cartoon. He says, "Well, I'll be. I guess the little chicken was right." So, one more thing I want to mention is a lot of talk is now about what do we do with the debris. I mentioned that we leave things as they are, the situation as it was. So one of the things you can do is go up and get the stuff that's already there and help it out of orbit Earth. It's what we call active debris removal. Keep your active debris. So what my colleague has done is made a model of this, where he goes and in the model goes and gets the stuff that's already there, based on schedule, based on how big the objects are, what they're in dangerous orbit, whatever, and gradually remove them. And I think he's got two scenarios. The blue is 2 per year, and the green is 5 per year. This is the big jump. This is orbital debris in low Earth orbit. This is the big jump from our collision. But as you can see, if you don't do anything, the environment continues to increase out for 200 years. But if you start getting stuff every year, so this takes 2 per year, you greatly modify. Now, if you can go up to 5 per year, you basically stop the growth of the stress. So there's a lot of interest in now, how do you go and get the stuff that's already there? Of course, there's a whole aspect of what do you, people who are launching stuff in the future cleaning up after themselves, but that's a whole other issue. Real quick, I had my colleagues send me this. Here's sort of target things you want to go after in terms of inclination and altitude. Based on his model, we can sort of make a list of what is the best target for the guy. There's a lot of various rocket bodies, many of the Russians, from all different countries, very massive, very long-lived orbits that would be best to get out of the environment. These are 500 objects at each other. And this is Russell's chart from Boeing. He's actually been looking at different things, lots of different ideas. One of them is the space tusk. You send a spacecraft up, and its purpose is to grab stuff into the orbit. For small debris, you're thinking about some sort of sweeper, some sort of passive sweeper. This turns out to probably not be a good idea, but maybe there's some way to do it. There's been talk of using airborne lasers or ground-based lasers to shoot down small debris. Basically, if the object comes over the horizon, you shine the laser on a blade, the front end, gas comes off, and we'll push. Keep doing that eventually. It turns out to be logistically very complex. The biggest problem with this one is any weapon that's strong enough to remove orbital debris is strong enough to do it. There's all sorts of international logistics. The other problem is by international treaties, UN treaties, the launching state owns an object. You can't just go up and remove a Russian rocket body without permission. So all the talk we've done and talk about doing demonstrations has always been go to American stuff. You don't have to get any legal permissions up front to take care of your own mess. All right, last chart, challenges remain. I didn't talk about it. We spent a lot of time coming up with what are standard mitigation guidelines. It turns out the best things you can do when you push for a long time is don't make messes in the first place. If you're going to abandon a rocket body in orbit, get rid of that energy source, the ones that turn into a bottom line. If you're going to be finished with your spacecraft, make sure it gets out of Earth orbit in a reasonable length of time. It's called 25 years. If it's got out in 25 years, that's a whole lot. So, mitigation guidelines. These are voluntary, put together by multiple spacefaring nations. However, despite efforts to reduce accidental explosions, they still occur. Accidents still happen. Still have this problem. People are developing new rocket bodies. As soon as they launch a new one, it has a new problem. Don't do what China did. I think they've learned a lesson. But don't make a mess you don't have to make. If you're going to do any satellite test, do it at a low altitude. And the last thing is that collision in 2009 is the harbinger of things. Collisions are going to dominate. Nothing, unless you start removing stuff actively from the environment, you'll see more collisions. Right now, the rate's about 1 in 10. But that's a statistic. So every year you have a 1% chance of having a collision. One of the things people are doing is a collision avoidance, but collision avoidance only works if your spacecraft's active, and only a tiny fraction of spacecraft are active. So how can we tell when man has officially conquered space? There we go. All right. Any other questions?
Yeah, once again, whenever you have a collision, and then the colliding particles are in orbits, how does it go from just an orbit to a sphere?
Well, what happens is in the center frame of the object, to a simple approximation, what we discovered, the debris comes off in basically isotropic direction, comes off as a sphere. But if the orbit's going this general direction, this one goes into a slightly higher orbit. It's like I got a little boost. And this one got retrofire. So this one's in a slightly lower orbit. This one's in a slightly higher orbit. And one that comes out this way is in a slightly different plane than the one that goes that way. And so over time, those diverge. And the first thing you see is in the period with that stretching out.
So the reason is, I guess, as soon as the collision occurs, then you have particles with different velocities.
Right. It's like each one got a little tiny rocket boost on it. Yeah. And like I said, what the interesting phenomenon is you don't seem to get much momentum transfer, which is sort of counterintuitive because we're used to momentum transfer. Objects bounce off each other. Literally, well, it's not exactly this way, but almost like we just have two separate explosions. Now, it turns out that I think the Chinese ASAT test did show a little bit of momentum transfer. The first time we've seen that phenomenon, actually, in tests, but it's very small. It's a tiny fraction of what you would expect from just your everyday type of things you do in the lab. But part of it is the hypervelocity. Apparently, hypervelocity is very, very momentum. Yes.
You mentioned about the laser can be used to destroy debris.
Well, not destroy it. It's to get it to drop out of orbit. Basically, to give it a little push.
Can be used in space.
Well, the problem with putting a laser on legally. Well, it's very complicated. But if you try to put a laser in space, problem is power. The idea is to do it on Earth where you have plenty of power, but you go and catch objects and come over. But that tends to make other countries uncomfortable. And I think that's probably insurmountable in the world we live in. Maybe far off in the future that may be a doable thing. But people get real sensitive about weapons that can potentially damage assets. Military or non-military. There are space laws. There actually are. Space law is a strange thing. There's not as many as you think. There's actually a few space laws. And people have tried to push forward weaponization of space issues. But it turns out it's very thorny problem. Very difficult to monitor that. No one can come up with a definition of what space is. I could argue that ICBMs are space weapons, but they transit space. So nobody even has a legitimate answer for what a space weapon is. I think what everybody agrees that certain things are space weapons. You put a platform in space with nuclear weapons aimed at the Earth, that is a space weapon. Everybody agrees. But the problem is that a lot of things that on the surface. So, and whenever you talk about legality, you've got to clearly define it. You have it.
Yeah, you talked about deorbiting the International Space Station at some point in the future. My question is that so much time, money, and effort has been put into building the International Space Station, and it's considered like one of the greatest achievements.
Right, like the pyramid.
Yeah, and it's like, why would you want to deorbit?
Well, at some point, it's going to get, just the fact of life, it is going to be, there's been so much time repairing the equipment on board, it simply can't do it. It can't do anything other than just constantly repair. At that point, it ends its useful life. It's like the car. Your car runs, you run the car, it runs great, but eventually it's going to get so expensive to maintain it, constantly repair it, that it's just not cost effective. You can't even use it. It becomes a lawn ornament or a garage ornament. And that's part of it. And the thing is, you don't just want to abandon it because it is going to be. And when it does re-enter, it will be a risk to people. So you want to do it, you want to dispose of it. And that's just the nature of it. That's why I mentioned at the beginning, everything is destined to become different. Whether we like it or not, if you think about every piece of technology you have, cars, television, refrigerator, your computer, your cell phone, one of these days is no longer going to be. That's just the way of the world. So, but whenever we talk about deorbiting, they always put it on this is far into the future. But we're planning now. We've got a plan now for decision. I think they're talking 2020. A long time down the road. But eventually it's going to have to be. And you have to start planning that.
Sorry?
I have another question. You said the paint lakes are not orbit. And what I was wondering is paint necessary for these satellites?
Yes and no. Yes and no. It turns out that I suspect much of the paint is actually from rockets. Rockets are painted with paint that's not space ready because the paint for the rockets is preserving when it's sitting on the ground in the rain, in the smog, to protect the surface when they launch. It's not designed because when they finish with the rocket, they discard it. The paint is not really designed to handle space and life. Every time it orbits the Earth, it goes through a thermal cycle. It's got so much oxygen, you said they are organic binders. Spacecraft have paint they use. Spacecraft have paint they use for thermal control. Spacecraft tend to be a little bit better. But even on spacecraft, when we went up to the Hubble, we thought it was carefully, there's paint flecking off the Hubble. And the people who designed that were astounded. Disintegrate. What do we do wrong? But it turns out that I think we ought to do a better job of telling people who design the spacecraft. Be careful how you prepare the surface of the paint. They don't even realize most of them is an issue. If they knew it was an issue, they'd be more careful.
First window that was placed on the show over with the titanium plate. We had a painting.
Yes.
The little crater on the outside. The problem was the depth of the tail, which we were concerned that it would fracture during the process.
The shuttle actually got toward the end, replacing a window every mission.
I know it, but the very first one was a painful.
Was it SPS-5? Was that the first one? There was a lot of concern that when you have these, just like in the car window, it damages the integrity of the window. I think this concern was actually on the next descent. They were worried about breaking.
What about breaking any parts?
Right. Actually, the panes are they actually have multi
The
panes.
loss of the thermal pain, they have,
Yeah.
but once you lose it, the interior stresses on, actually not on the glass itself, but the thermal stress on the engine, cause the paint cracks and breaks.
It's kind of interesting that if paint is such an issue, why isn't it addressed in the peaceful uses for outer space trees?
Well, I don't think they speak to use outer space as a whole. It is addressed to some extent in the mitigation plan. However, the real issue of paint is it's really not a driving issue because the paint particles tend to be very, very small, less than 1 millimeter. They typically are only dangerous to very, very sensitive spaces. That would be windows on human spacecraft, astronauts on human spacecraft. The much more serious risk, I believe, in people's minds, is not the right, but different, I don't know, is larger objects that can cause actually penetration of crew, actually cause a hole in the wall which could lose the crew. And those are quite a bit larger objects. But they can be medium-sized objects on the shuttle. The wrong spot. We actually had hits on the shuttle, I can paper one, that we had a hit over here, that if it had hit here, we would have lost it. Forget about models and everything. If that would have hit there, we would have had here. Fortunately, here is small, and that's big, but it hit there. Could have just moved to hit there. Any other thoughts?
Let's thank our speaker. And I guess I'll see you guys here next Tuesday. We're going to have another talk with David Black about extraterrestrial life.
Yeah.
And so,
I've got a quick extraterrestrial life story for you. I had a colleague that analyzed the craters on one of the surfaces from LDAP. And one late night, he was looking at one of the craters, and he realized that in the crater was an odd structure. It looked for all the world like a tiny skeleton. And he went home that night. That's organic, something he couldn't sleep that night. And he went back the next day and looked closer, and it turned out it was actually a piece of diatomaceous earth. So it was proof of life, and it was in space, but it wasn't extraterrestrial. Because diatomaceous earth is a white powder that's from skeletons of tiny creatures that live in the ocean, and it was put in some paint, launched into space, and then it hit it on that. So that's my life at outer space story. He thought, for a moment there, he thought he had the Nobel Prize.
Who was that?